Tonight, we're going to discover something that will completely change how you picture the solar system. You've seen the diagrams. The sun in the middle, 8 planets orbiting around it, maybe a few comets and asteroids scattered in between. And then after Neptune, it just ends. Empty space, nothing. But here's what those diagrams never show you. The solar system doesn't end at Neptune, it doesn't even end close to Neptune. There is a structure out there so unimaginably vast, so impossibly far from the sun, that it makes the entire planetary region look like a tiny dot at the center of something enormous. It's called the Oort Cloud, and when you understand its true scale, you'll realize the solar system is thousands of times larger than you ever imagined. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you already know. The solar system. You learned about it in school. You've seen the posters on classroom walls and the diagrams in textbooks. The sun sits in the middle, big and bright. Then the planets orbit around it in neat circles. Mercury, Venus, Earth, Mars, then the asteroid belt, then the gas giants, Jupiter, Saturn, Uranus, Neptune, and after Neptune, the diagram just stops. There's nothing else, maybe a few comets drawn with little tails streaking across the background for decoration, but that's it. The solar system ends. You move on to the next chapter. That picture is so familiar, so deeply embedded in how most people think about space, that it feels like the truth. It feels complete, but it's not. That diagram you grew up with is one of the most misleading images in all of science education. Not because it's wrong about what it shows, but because of what it leaves out. What it leaves out is almost everything. To understand why, we need to start from the beginning. We need to build the solar system from the inside out, step by step, layer by layer, paying attention to the actual distances involved. Because the distances are where the surprise hides. The distances are what the diagrams get catastrophically wrong. And once you see the real numbers, once you understand what they actually mean, you will never look at those neat little classroom posters the same way again. Let's begin at the center. The sun. It's a star. A massive ball of hydrogen and helium undergoing nuclear fusion at its core. The sun's diameter is about 864,000 miles. It contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust, all of it combined makes up just 0.14% of the total mass. The sun is not just the center of the solar system. It is the solar system, at least in terms of mass. Everything else is almost a rounding error. Now let's move outward. Mercury, the closest planet to the sun, orbits at an average distance of about 36 million miles. That's roughly 0.4 astronomical units. An astronomical unit, or AU, is the average distance from the Earth to the sun, about 93 million miles. Astronomers use this unit constantly because it gives a convenient scale for measuring distances within the solar system. 1 AU is a big distance by human standards. Light takes about 8 minutes and 20 seconds to travel from the sun to the Earth. If you could somehow drive a car at highway speed toward the sun, it would take you over 170 years to get there. That's the distance from Earth to the sun, 1 AU. Remember that number because we're going to need it later, and by the end of tonight, 1 AU is going to feel incredibly, almost laughably small. Venus orbits at about 0.7 AU from the sun. Earth, of course, is at 1 AU. Mars sits at roughly 1.5 AU. These 4 planets, Mercury, Venus, Earth, and Mars, are the rocky planets, the terrestrial worlds. They're all relatively close to the sun, all within about 1.5 AU. They're small, dense, and made of rock and metal. They have solid surfaces you could theoretically stand on, though you wouldn't want to stand on Venus with its 900-degree surface temperature and crushing atmospheric pressure, or on Mercury with its wild temperature swings from over 800 degrees in sunlight to nearly -300 in shadow. Between Mars and Jupiter lies the asteroid belt. Most people imagine the asteroid belt as a dense field of tumbling rocks, like something out of a science fiction movie where spaceships have to dodge boulders at every turn. The reality is completely different. The asteroid belt is mostly empty space. If you flew a spacecraft through it, you'd be unlikely to see a single asteroid with the naked eye. The distances between individual asteroids are enormous. The entire mass of the asteroid belt, every rock and pebble combined, is less than 4% of the mass of Earth's moon. It's not a wall or a barrier. It's a sparse scattering of debris left over from the solar system's formation. Material that never managed to coalesce into a planet because Jupiter's immense gravity kept stirring it up, preventing the pieces from coming together. The asteroid belt extends from roughly 2.2 to 3.3 AU from the Sun. Beyond it, we enter the realm of the giant planets. And this is where distances start to stretch in ways that catch most people off guard. Jupiter, the king of the planets, orbits at about 5.2 AU from the Sun. That's 5 times farther from the Sun than Earth is. Jupiter is enormous. Its diameter is about 86,881 miles, roughly 11 times wider than Earth. You could fit over 1,300 Earths inside Jupiter's volume. It has at least 95 known moons, including 4 large ones discovered by Galileo in 1610 that are worlds in their own right. Jupiter is so massive that it contains more than twice the mass of all the other planets in the solar system combined. Its gravity shapes the orbits of asteroids and comets throughout the solar system. Some scientists believe Jupiter has acted as a gravitational shield for Earth over billions of years, deflecting or capturing objects that might otherwise have struck our planet. Saturn orbits at about 9.5 AU, nearly 10 times farther from the Sun than Earth. Saturn is famous for its magnificent ring system, made of countless particles of ice and rock ranging from tiny grains to chunks the size of houses. The rings extend tens of thousands of miles from the planet but are astonishingly thin, in most places only about 30 feet thick. Saturn itself is nearly as large as Jupiter, with a diameter of about 72,367 miles. It has at least 146 known moons. Its largest moon, Titan, is bigger than the planet Mercury and is the only moon in the solar system with a thick atmosphere. Titan has lakes and seas on its surface, not of water, but of liquid methane and ethane. Rain falls from Titan's sky, carves river channels into the surface, and collects in low-lying basins. It's one of the most alien yet strangely Earth-like worlds we know of. Already, at Saturn's distance, the Sun has become noticeably dimmer. If you stood on one of Saturn's moons and looked back at the Sun, it would still be the brightest object in the sky by far, but it would appear about 100 times fainter than it does from Earth. Sunlight at Saturn takes about 1 hour and 20 minutes to arrive. When the Cassini spacecraft was orbiting Saturn from 2004 to 2017, every command sent from Earth took over an hour to reach it. Every image the spacecraft took needed over an hour to travel back to Earth at the speed of light. Real-time control was impossible. Engineers had to plan sequences of commands days or weeks in advance and trust that the spacecraft would execute them correctly. Uranus orbits at about 19.2 AU from the Sun, nearly 20 times farther than Earth. Uranus is an ice giant, smaller than Jupiter and Saturn, but still enormous compared to Earth. About 63 Earths could fit inside Uranus. The planet is tilted almost completely on its side, with its axis of rotation nearly parallel to its orbital plane. This means its poles sometimes point almost directly at the Sun. One pole gets 42 years of continuous sunlight, followed by 42 years of continuous darkness. No one is entirely sure why Uranus is tilted so dramatically. But the leading theory is that a massive collision early in the solar system's history knocked it over. Neptune is the outermost planet, orbiting at about 30 AU from the Sun, 30 times farther than Earth. Light from the Sun takes over 4 hours to reach Neptune. At this distance, the Sun is so far away that it appears roughly 900 times dimmer than it does from Earth. It's still the brightest point of light in Neptune's sky, brighter than any star, but it's no longer the overwhelming source of light and warmth that it is for the inner planets. Neptune is a cold, dark, windy world. Wind speeds on Neptune reach up to 1,200 miles per hour, the fastest measured on any planet in the solar system. Its largest moon, Triton, orbits backward relative to the planet's rotation, suggesting it was captured from the Kuiper Belt rather than forming alongside Neptune. Now, here's where most people's mental map of the solar system ends. Neptune at 30 AU. That's the last planet. The textbook closes. The poster on the wall has run out of space. But the solar system does not end at Neptune. Not even close. What lies beyond Neptune is where the story truly begins to get strange, and where the scale of the solar system starts to reveal itself as something far more vast than those classroom diagrams ever suggested. Beyond Neptune's orbit, starting at roughly 30 AU and extending outward to about 50 AU, lies a region called the Kuiper Belt. The Kuiper Belt is a broad, flattened ring of icy objects orbiting the Sun in roughly the same plane as the planets. Think of it as a much larger, much more massive version of the asteroid belt, but made of ice instead of rock. While the asteroid belt contains mostly rocky debris left over from the inner solar system's formation, the Kuiper Belt contains frozen remnants from the outer solar system. These objects are composed of ices like frozen water, methane, and ammonia mixed with rock and dust. They're the leftovers from the formation of the giant planets, material that was too spread out and too far from the Sun to coalesce into a planet. The most famous Kuiper Belt object is Pluto. Discovered in 1930 by Clyde Tombaugh, Pluto was considered the 9th planet for 76 years until 2006, when the International Astronomical Union redefined what constitutes a planet. Pluto didn't make the cut because it hasn't cleared its orbit of other debris. It's one object among many in the Kuiper Belt, not a dominant gravitational presence in its region of space the way the 8 planets are in theirs. Pluto has a diameter of only about 1,473 miles. It's smaller than Earth's moon. When NASA's New Horizons spacecraft flew past Pluto in July 2015, after a 9.5-year journey, it revealed a surprisingly complex world. Mountains of water ice, thousands of feet tall, vast plains of frozen nitrogen, a thin atmosphere extending much farther than expected. A large heart-shaped region now named Tombaugh Regio, after Pluto's discoverer. Pluto turned out to be far more interesting than anyone had anticipated, but Pluto is not alone out there. The Kuiper Belt contains thousands of known objects, and astronomers estimate there may be hundreds of thousands of objects larger than 60 miles across, along with trillions of smaller ones. Several other large Kuiper Belt objects have been discovered, including Eris, which is roughly the same size as Pluto and actually slightly more massive. The discovery of Eris in 2005 was one of the key factors that led to Pluto's reclassification. If Pluto was a planet, then Eris had to be a planet too, and so did several other large Kuiper Belt objects. Rather than continually adding new planets to the list, astronomers created the dwarf planet category. Other notable Kuiper Belt objects include Marke and Haumea, both classified as dwarf planets. Haumea is particularly unusual because it's shaped like an elongated ellipsoid, stretched out by its rapid rotation. It spins so fast that it completes one rotation in under 4 hours, which has pulled it into a shape resembling an egg or a squashed football. It also has a faint ring system, one of only a handful of objects besides the giant planets known to have rings. The Kuiper Belt was long suspected to exist before it was confirmed by observation. In 1951, astronomer Gerard Kuiper suggested that a belt of icy bodies might exist beyond Neptune, though his specific predictions about the belt's properties turned out to be somewhat different from what was eventually found. The first Kuiper Belt object other than Pluto and its moon Charon was discovered in 1992 by astronomers David Jewett and Jane Liu. They found a small faint object designated 1992 QB1, orbiting the Sun at about 44 AU. This discovery confirmed that the region beyond Neptune was not empty. It was populated by a vast collection of frozen bodies, remnants from the earliest days of the solar system. Now, the Kuiper Belt is genuinely far from the Sun. At 50 AU, you are 50 times farther from the Sun than Earth is. Sunlight takes nearly 7 hours to reach this distance. The Sun from out there would appear as a brilliant star, still the brightest object in the sky by a significant margin, but no longer a disk. You would need a telescope to see the Sun as anything other than a very bright point of light. The temperature out there is brutally cold, hovering around -370 degrees Fahrenheit. Icy bodies in the Kuiper Belt have been frozen solid for billions of years, preserved in a deep freeze since the solar system's formation 4.5 billion years ago. They're time capsules, containing pristine material from the earliest days of the solar system. The Kuiper Belt was, for a time, considered by many to be the outer edge of the solar system. After all, it's beyond all the planets. It's incredibly far from the Sun. Objects out there are so faint that we can barely detect them, even with our most powerful telescopes. It seemed reasonable to think that the solar system simply ended somewhere around 50 AU, fading into the emptiness of interstellar space. But this assumption was wrong. Spectacularly wrong. The Kuiper Belt is not the edge of the solar system. It's not even close to the edge. In fact, the Kuiper Belt, as far as it is, occupies only a tiny sliver of the Sun's true domain. Beyond the Kuiper Belt, there is an almost unimaginable amount of space that still belongs to our star. The Kuiper Belt at 30 to 50 AU is, in a very real sense, still right next to the Sun compared to what lies farther out. To begin to see why, consider this. The Kuiper Belt extends to roughly 50 AU from the Sun. That's the farthest region of the solar system that we've directly explored with spacecraft, and directly observed with telescopes. Beyond that, our knowledge becomes much more indirect. We haven't sent spacecraft out there. We can't see individual objects out there with any telescope currently in existence. But we know something is out there because it keeps sending us messages. Those messages come in the form of comets. Comets are among the most spectacular and mysterious objects in the solar system. They're small bodies made of ice, dust, and rock, often described as dirty snowballs or icy dirt balls depending on the ratio of ice to rock. When a comet's orbit brings it close to the Sun, the ice begins to sublimate, turning directly from solid to gas. This creates the comet's characteristic coma, a fuzzy envelope of gas and dust surrounding the solid nucleus, and its tail, which can stretch for millions of miles across space, always pointing away from the Sun because it's pushed by the solar wind and radiation pressure. Comets have fascinated and terrified humans for thousands of years. Ancient civilizations saw them as omens, signs of impending disaster or divine displeasure. The appearance of a bright comet was often recorded alongside wars, famines, and the deaths of kings. Today, we understand that comets are simply chunks of ancient ice following elongated orbits around the Sun. But they remain objects of intense scientific interest because they preserve material from the solar system's formation, material that has been frozen and largely unchanged for 4.5 billion years. Here's what's crucial for our story. Astronomers have noticed that comets come in two distinct types, based on their orbits. Short-period comets have orbital periods of less than 200 years. They tend to orbit in roughly the same plane as the planets, moving in the same direction. Their orbits are relatively modest in size, typically extending out to somewhere around the Kuiper Belt. Halley's Comet, the most famous comet of all, is a short-period comet with an orbital period of about 75 to 79 years. It last appeared in 1986 and will return around 2061. Short-period comets are thought to originate from the Kuiper Belt. Gravitational interactions with Neptune occasionally nudge a Kuiper Belt object onto an orbit that brings it closer to the Sun, transforming it from a dormant frozen body into an active comet with a visible tail. But then there are the long-period comets. These are different, very different. Long-period comets have orbital periods of more than 200 years. Some have orbital periods of thousands of years. Some have orbital periods of millions of years. Their orbits are typically extremely elongated, plunging close to the Sun and then retreating to enormous distances before slowly falling back again. And here's the key detail. Long-period comets come from all directions. They don't stick to the plane of the planets like short-period comets do. They arrive from above, below, and every angle in between. Their orbits are randomly oriented in 3 dimensions. Some orbit in the same direction as the planets. Others orbit in the opposite direction. There's no pattern, no preferred plane, no preferred direction. They come from everywhere. This tells astronomers something profound. Wherever these comets are coming from, it's not the Kuiper Belt. They're arriving from too many directions, from too far away, with orbits too random and too elongated to originate from that flat ring of icy debris beyond Neptune. They're coming from somewhere else, somewhere much farther out, somewhere that nobody in the mid-20th century had ever directly seen. And when one brilliant astronomer finally sat down and worked out exactly where that somewhere had to be, the answer changed everything about what we think the solar system is. It changes the size, it changes the shape, it changes the boundaries. It takes that neat little diagram from your school textbook, the one with the Sun in the middle and the planets in their tidy orbits, and it reveals it to be a picture of only the very innermost core of something thousands of times larger. The planets, the asteroid belt, the Kuiper Belt, everything you've ever seen in a diagram of the solar system, all of it fits within roughly 50 AU of the Sun. The Oort Cloud may extend to 100,000 AU. That's 2,000 times farther. Everything you thought was the solar system is less than 0.1% of the Sun's true gravitational domain. The region of space controlled by our star is not a compact disk of orbiting planets. It is an enormous, roughly spherical volume of space, stretching in every direction for trillions of miles. And almost all of that volume, almost all of that territory, belongs to the Oort Cloud. But before we can understand the Oort Cloud's true scale, before we can grasp just how far it extends and what that means for our picture of the solar system, we need to understand how we know it exists at all. Because here's the thing. No one has ever seen the Oort Cloud. We've never seen it. Not directly. Not with any telescope or any spacecraft. Everything we think we know about the Oort Cloud has been pieced together from clues, from the behavior of objects that occasionally fall inward from that vast distance. It's deduced from the behavior of comets that fall inward from that immense distance, like messages in bottles washing up on a shore, telling us about a place we've never visited and cannot directly see. The story of how scientists figured out that this invisible, unobservable structure must exist is one of the great detective stories in the history of astronomy. And it begins with a Dutch astronomer in the middle of the 20th century who looked at the orbits of comets and realized they were telling him something extraordinary about the hidden architecture of the solar system. Something no one had seen before. Something that would force astronomers to completely rethink how large the solar system really is. And when you hear what he found, when you understand the reasoning that led to the Oort Cloud's discovery, you'll begin to see why the solar system is not the compact, well-defined structure you were taught it was. It is something far stranger, far more vast, and far more mysterious than any textbook has ever shown you. The year was 1950. The Second World War had ended just 5 years earlier. Europe was still rebuilding. The Cold War was beginning to reshape global politics. And in the Netherlands, a quiet, meticulous astronomer named Jan Hendrik Oort was about to change our understanding of the solar system forever. Not by discovering a new planet, not by building a new telescope, but by sitting down with a list of comet orbits and thinking very carefully about what they were telling him. Jan Oort was already one of the most respected astronomers in the world by that point. He had done groundbreaking work on the structure and rotation of the Milky Way galaxy. His studies of how the galaxy rotates had helped confirm that the Sun was not at the center, as earlier generations had assumed, but was located about 2/3 of the way out from the center in one of the spiral arms. He understood large-scale structures. He understood how gravity shapes the motion of objects across enormous distances. And when he turned his attention to comets, he brought that same ability to see patterns in data that others had overlooked. The puzzle Oort was trying to solve was straightforward but deeply important. Where do long-period comets come from? By the middle of the 20th century, astronomers had catalogued the orbits of many comets. Short-period comets, the ones that return every few decades or centuries, were reasonably well understood. They orbited in the same general plane as the planets, moved in the same direction, and had orbits that didn't extend too far from the Sun. They seemed to come from a reservoir somewhere in the outer solar system, what we now know as the Kuiper Belt. But long-period comets were a mystery. These comets had orbital periods of thousands or even millions of years. Their orbits were extremely elongated, stretching far beyond anything in the known solar system. And critically, they arrived from every direction, not just from the plane of the planets, but from above, below, and every angle in between. Their orbital orientations appeared completely random. Oort gathered data on the orbits of long-period comets and made a remarkable observation. When he looked at the farthest points of their orbits, the aphelion distances where the comets reached their maximum distance from the Sun before falling back inward, he noticed something striking. A large number of these comets had aphelion distances clustered around a specific range, roughly 20,000 to 50,000 AU from the Sun. Some extended even farther. But there was a clear concentration of comets whose orbits reached out to these enormous distances. This was significant. If long-period comets were simply random objects flying through the solar system from interstellar space, their orbits wouldn't cluster at any particular distance. They'd have all sorts of random trajectories, but the clustering suggested something different. It suggested that these comets were not interstellar visitors. They were members of the solar system. They were gravitationally bound to the Sun, and they were coming from a specific region, an enormous spherical shell of icy bodies surrounding the Sun at distances of tens of thousands of astronomical units. Oort also noticed something else that was crucial. The orbits of these long-period comets were not quite stable. Every time a comet falls inward toward the Sun and passes through the inner solar system, it interacts gravitationally with the giant planets, especially Jupiter. These gravitational encounters change the comet's orbit. Sometimes they speed the comet up, sending it on a trajectory that will take it even farther from the Sun on its next pass. Sometimes they slow it down, tightening its orbit. And sometimes they eject the comet from the solar system entirely, flinging it into interstellar space, never to return. The key insight was this. Over millions of years, these gravitational interactions with the planets should gradually deplete the supply of long-period comets. Comets that fall inward get their orbits altered. Many are lost, either ejected from the solar system or captured into shorter-period orbits. If there were no mechanism to replenish the supply, we should have run out of long-period comets long ago. The solar system is 4.5 billion years old. That's more than enough time for the original supply to be exhausted. But we haven't run out. Long-period comets keep appearing. New ones are discovered regularly. The supply is being replenished somehow. This meant there had to be a vast reservoir of icy bodies at enormous distances from the Sun. A reservoir so large that, even after billions of years of slow depletion, it still contained enough objects to keep sending comets our way. And this reservoir had to be spherical, not flat, because the comets arrive from all directions equally. This was Oort's great deduction. Working backward from the observed orbits of comets, he concluded that the solar system must be surrounded by an enormous, roughly spherical cloud of icy objects at distances of tens of thousands of AU. These objects orbit the Sun so slowly and at such vast distances that they're essentially in cold storage, frozen relics from the earliest days of the solar system. Occasionally something disturbs them. A passing star's gravity, the tidal pull of the Milky Way galaxy itself, or some other gravitational perturbation nudges an object out of its stable orbit. It begins to fall inward, slowly at first, then faster as it approaches the Sun. By the time it reaches the inner solar system, it's moving fast, its ices beginning to sublimate in the Sun's warmth, producing the glowing coma and streaming tail that we recognize as a comet. It swings around the Sun, briefly becomes visible from Earth, then heads back out into the darkness on its long, lonely return journey to the outer reaches of the solar system. A round trip that might take millions of years. Oort published his hypothesis in 1950, and it was immediately recognized as one of the most important ideas in planetary science. The cloud of icy bodies he proposed was named the Oort Cloud in his honor. And over the decades since then, further observations have only strengthened the case for its existence. Every long-period comet that arrives from an unexpected direction, every comet with an orbit that reaches out to tens of thousands of AU, adds another data point supporting Oort's original reasoning. Some of the most spectacular comets in living memory have been messengers from this distant reservoir. Comet Hyakutake, which blazed across the night sky in 1996, had an orbital period estimated at roughly 70,000 years. Its orbit stretched so far from the Sun that it reached deep into the outer Oort cloud before turning back. Just a year later, Comet Hale-Bopp appeared, one of the brightest comets of the 20th century, visible to the naked eye for a record 18 months. Hale-Bopp's orbit carries it far beyond the Kuiper Belt into the distant outer reaches of the solar system. These were not abstract data points on an astronomer's spreadsheet. They were objects that millions of people stepped outside to see, brilliant visitors trailing glowing tails across the darkness, each one carrying physical proof that an enormous unseen structure exists far beyond the planets. But here's what you have to understand clearly. The Oort cloud has never been directly observed. No telescope on Earth or in space has ever seen an Oort cloud object sitting out there in that distant shell. These objects are far too small, far too faint, and far too distant to detect with any instrument we currently possess or are likely to possess in the foreseeable future. An Oort cloud object might be a few miles across, made of dark ice and rock, sitting tens of thousands of AU from the Sun in the cold darkness of near interstellar space. At that distance, even the largest Oort cloud objects would be billions of times too faint to see. We don't see the Oort cloud, we infer it. We deduce its existence from the comets it sends our way, like detectives reconstructing a crime from the evidence left behind. The comets are the evidence. The Oort cloud is the conclusion. This makes the Oort cloud one of the most extraordinary objects in astronomy. It is, by many measures, the largest structure in the solar system. It dominates the solar system's volume, and yet it has never been seen. Its existence rests entirely on indirect evidence and logical reasoning. This is science at its most powerful and most humbling. We can figure out that something enormous exists even though we can't see it, simply by carefully observing what it does. So what is the Oort cloud physically? What does it actually look like? Or more accurately, what would it look like if you could somehow see it? The answer is that it wouldn't look like much of anything. The Oort cloud is not a dense shell or a thick wall of material. It's not like the rings of Saturn, where particles are packed close together in a visible structure. The Oort cloud is incredibly, almost absurdly sparse. It's a vast, diffuse collection of icy objects spread across an enormous volume of space, with each object separated from its nearest neighbor by enormous distances. If you were somehow transported to the middle of the Oort Cloud, you would see nothing unusual. Space would look empty in every direction. There would be no visible sign that you were inside a vast structure containing trillions of objects. No haze, no glow, no sense of enclosure, just darkness and distant stars indistinguishable from any other patch of deep space. And the Oort Cloud objects themselves, you wouldn't see any of them, not one. They'd be scattered so thinly across such a vast volume that the nearest one might be billions of miles away from you. Even if you knew exactly where to look, it would appear as nothing more than a faint point of light, indistinguishable from a distant star, if you could see it at all. The Oort Cloud is a cloud in name only. It's not a fog or a mist or a haze. It's a scattering of tiny objects in an ocean of emptiness, like a handful of sand grains scattered across an area the size of a continent. Let me give you a sense of the numbers involved. Astronomers estimate that the Oort Cloud may contain somewhere between several hundred billion and a few trillion icy objects larger than about half a mile across. That sounds like a lot, and it is a lot of objects. But the volume of space they occupy is so staggeringly large that even trillions of objects amount to almost nothing. The average distance between neighboring Oort Cloud objects might be hundreds of millions of miles, perhaps close to a billion. Each object is a tiny frozen world drifting through space in almost perfect isolation, separated from its nearest companion by a gulf so vast that it would take a spacecraft years or even decades to cross at high speed. To put this in perspective, imagine shrinking the Oort Cloud down so that each icy object was the size of a grain of sand. Even at this reduced scale, the nearest grain of sand to any other grain would be miles away. The Oort Cloud is overwhelmingly, crushingly empty. It is a void with occasional punctuation marks scattered through it at intervals so large that the word sparse doesn't begin to capture it. And yet, despite this extreme emptiness, the total mass of the Oort Cloud is thought to be substantial. Estimates vary widely because we can't directly observe it, but most calculations suggest the Oort Cloud contains somewhere between 1 and a few tens of Earth masses worth of material. Some estimates go higher, suggesting it could contain up to 40 Earth masses. That's a lot of material, and almost all of it is ice. Water ice, methane ice, ammonia ice, carbon dioxide ice, mixed with rock and dust. These are the building blocks of the outer solar system, primordial material left over from the formation of the Sun and planets 4.5 billion years ago. But this raises a natural question. How did all that material get out there? The Oort Cloud sits at distances of thousands to tens of thousands of AU from the Sun. The planets formed much closer in, within about 30 AU. How did icy objects that presumably formed in the same general region as the planets end up so impossibly far away? The answer lies in the gravitational influence of the giant planets, particularly Jupiter, Saturn, Uranus, and Neptune. During the early solar system, roughly 4 to 4.5 billion years ago, the region around the giant planets was crowded with billions of small icy bodies, the planetesimals left over from the formation of the planets. These planetesimals orbited the Sun in the same general region as the giant planets, roughly 5 to 30 AU out. But they didn't stay there. The giant planets' gravity was constantly tugging on them, changing their orbits with every close encounter. Some planetesimals were flung inward toward the Sun, where they either fell into the Sun, hit one of the inner planets, or were ejected from the solar system entirely. But many were flung outward, away from the Sun, onto long, elongated orbits that took them far into the outer reaches of the solar system. This process is called gravitational scattering, and it was incredibly efficient. Over the course of a few 100 million years, the giant planets cleared out most of the icy debris in their vicinity by scattering it in all directions. Now, you might expect that objects flung outward by the giant planets would simply escape the solar system entirely, flying off into interstellar space, and many of them did, but not all. Some were flung outward with just the right amount of energy to reach enormous distances from the Sun, without quite escaping the sun's gravitational hold. They ended up on extremely elongated orbits, taking them thousands or tens of thousands of AU from the sun before slowly falling back. These objects were in a kind of gravitational limbo, not quite free of the sun's gravity, but so far away that the sun's pull was incredibly weak. And here's where something subtle but important happened. At these enormous distances, other gravitational influences came into play. The gravity of passing stars, the tidal pull of the Milky Way galaxy as a whole, and the cumulative gravitational nudges from the overall distribution of mass in the galaxy slowly altered the orbits of these distant objects. These external influences randomized the orbits, gradually transforming them from the elongated, planar orbits they originally had into more circular, randomly oriented orbits. The objects that started out moving in the plane of the planets, scattered outward by Jupiter and the other giant planets, slowly had their orbits tilted, twisted, and rounded by the gentle but persistent tug of the galaxy. Over hundreds of millions of years, this process transformed a scattered disk of icy objects into a roughly spherical cloud. The original disk-like structure was erased. The objects ended up orbiting the sun in all directions, at all angles, forming the spherical shell we now call the Oort Cloud. The galaxy itself sculpted the Oort Cloud into its current shape. This formation scenario explains several things about the Oort Cloud. It explains why the cloud is spherical rather than flat. The initial scattering by the planets would have produced a more flattened structure, but galactic tides and stellar perturbations puffed it out into a sphere. It explains why Oort Cloud objects are made of ice. They formed in the cold outer regions of the solar system, where temperatures were low enough for ices to condense. It explains why the Oort Cloud is so far from the sun. The objects were scattered outward by the giant planet's gravity and ended up at the distances where the sun's gravity was just barely strong enough to hold onto them. It also explains something called the Inner Oort Cloud, or Hills Cloud, named after astronomer Jack Hills, who proposed its existence in 1981. The Inner Oort Cloud is thought to be a denser, more disk-like structure closer to the sun than the Outer Oort Cloud. It may begin at around 2000 AU and extend to about 20,000 AU. Objects in the Inner Oort Cloud are thought to be closer and more numerous than those in the Outer Cloud, but still far too distant to observe directly. The Inner Oort Cloud represents objects that were scattered outward by the giant planets, but didn't travel quite far enough to be strongly affected by galactic tides and passing stars. Their orbits weren't randomized as thoroughly as the Outer Oort Cloud objects, so they retained more of their original flattened distribution. The Inner Cloud may actually contain more objects than the Outer Cloud. Some estimates suggest it could hold 5 to 100 times more material, but because its objects orbit closer to the sun, where the sun's gravity is stronger, they're less likely to be dislodged and sent inward as comets. The Outer Oort Cloud, despite potentially containing fewer objects, is more vulnerable to gravitational perturbations, and is thought to be the primary source of long-period comets. The picture that emerges is of a layered structure. The Kuiper Belt sits closest, a flat ring of icy bodies extending from roughly 30 to 50 AU. Beyond that, starting at perhaps a few hundred AU, space becomes increasingly empty. Then, at around 2000 AU, the Inner Oort Cloud begins. A thick disk of icy bodies that gradually transitions into the Outer Oort Cloud. A vast spherical shell extending to somewhere around 50,000 to 100,000 AU. The entire structure is like a series of nested shells, each one larger and more diffuse than the last, each one containing material from the solar system's earliest days. What are these Oort Cloud objects actually made of? Since we've never directly observed one in the Oort Cloud itself, our best information comes from studying the comets that fall inward from it. When a long-period comet approaches the sun and begins to warm up, its ices sublimate and release gas and dust that we can analyze spectroscopically. These observations tell us that comets contain water ice as their primary volatile component. along with frozen carbon dioxide, carbon monoxide, methane, ammonia, and various organic molecules. The solid component is a mixture of silicate minerals, metals, and complex organic compounds. Some comets contain amino acids, the building blocks of proteins, suggesting that the ingredients for life were present in the solar system from its very earliest days. The composition of comets is thought to be essentially unchanged from the material in the original solar nebula, the cloud of gas and dust from which the solar system formed. At the enormous distances of the Oort Cloud, temperatures are so close to absolute zero that chemical reactions essentially stop. These objects have been frozen in a deep freeze for 4.5 billion years. They're among the most pristine samples of primordial solar system material that exist anywhere. If we could somehow retrieve an Oort Cloud object and study it in a laboratory, it would be like opening a time capsule from the birth of the solar system. The sizes of Oort Cloud objects are thought to range from tiny fragments less than a mile across to bodies perhaps a few hundred miles in diameter. Most are probably small, just a few miles across, similar in size to the nuclei of known comets, but there may be some larger objects out there. Some astronomers have speculated that the hypothetical planet, sometimes called Planet 9, a large undiscovered body that some orbital evidence suggests might exist in the outer solar system, could be orbiting in the inner reaches of the Oort Cloud. This remains highly speculative. No such object has been detected despite extensive searches, but the possibility illustrates how much we don't know about this vast, unexplored region. The gravitational perturbations that send Oort Cloud objects falling inward toward the Sun come from several sources. Passing stars are one of the most important. The Sun is moving through the Milky Way galaxy, and other stars regularly pass within a few light years of us. When a star passes close enough, its gravity can disturb objects in the outer Oort Cloud, changing their orbits. Some are pushed outward and escape the solar system entirely. Others are nudged inward, onto orbits that bring them close to the Sun. These become the long-period comets we observe. The frequency of these stellar encounters is not trivial. Over millions of years, many stars drift close enough to the Sun to tug on the outer Oort Cloud, and occasionally one passes near enough to disturb it significantly. A star passing within a few thousand AU of the Sun could disrupt the entire outer Oort Cloud, potentially sending a shower of comets cascading into the inner solar system. Some scientists have proposed that comet showers triggered by close stellar passages might be linked to mass extinction events on Earth, though this remains a topic of active debate and has not been conclusively demonstrated. The tidal force of the Milky Way galaxy itself is another important source of perturbation. The galaxy is not a uniform distribution of mass. It has a disk, a bulge, spiral arms, and a dark matter halo. The gravitational pull of all this matter creates tidal forces that act on the orbits of Oort Cloud objects. These forces are extremely gentle, far too weak to affect anything in the inner solar system. But at the enormous distances of the outer Oort Cloud, where the Sun's gravity is incredibly feeble, even these gentle galactic tides can slowly change orbits over millions of years. The galactic tide is actually thought to be the dominant mechanism for feeding comets from the outer Oort Cloud into the inner solar system, even more important than passing stars. Molecular clouds, dense concentrations of gas and dust in the galaxy, may also play a role. When the solar system passes through or near a giant molecular cloud during its orbit around the galactic center, the cloud's gravity can disturb the Oort Cloud much like a passing star would, but potentially on a larger scale, because molecular clouds are much more massive than individual stars. The Sun orbits the galactic center roughly every 225 to 250 million years. And during each orbit, it passes through regions of varying stellar density and occasionally encounters molecular clouds. These encounters might trigger episodes of enhanced comet activity, sending more objects than usual falling inward from the Oort Cloud. There's something deeply poetic about this picture. The Oort Cloud is a boundary zone between the solar system and the galaxy. It's the place where the sun's influence fades and the galaxy's influence begins. Objects in the outer Oort Cloud are held by the sun's gravity so loosely that the gentlest push from a passing star or the faintest tidal tug from the galaxy can send them on a journey inward. They're the solar system's most tenuous members, barely held, easily lost, drifting at the edge of our star's gravitational reach. They're more like distant acquaintances than close family, connected to the sun by the thinnest gravitational thread, always at risk of being pulled away by some external force. And every long-period comet you've ever seen in the night sky, every photograph of a comet with its glowing tail streaking across the darkness, began its journey as one of these distant, frozen objects. It drifted in the cold for millions or billions of years. Then something disturbed it. A nearby star's gravity, a galactic tide, some gentle push that was just enough to change its orbit. And it began to fall. Slowly at first, imperceptibly slowly, drifting inward across distances so vast that the journey itself took millions of years. Past the inner Oort Cloud, past the vast empty space between the Oort Cloud and the Kuiper Belt, past the Kuiper Belt, past the orbits of Neptune and Uranus and Saturn and Jupiter, until finally it reached the inner solar system, close enough to the sun for its ancient ices to begin warming for the first time in billions of years. The ice sublimated. Gas and dust poured off the surface. A coma formed. A tail appeared. And for a few weeks or months, this tiny frozen visitor from the outermost reaches of the solar system became visible from Earth, a glowing streak in the night sky, carrying with it a message from the edge of our sun's domain. That message is what told Jan Oort in 1950 that the solar system is far larger than anyone had realized. That message is what tells us today that beyond the planets, beyond the Kuiper Belt, beyond everything we can directly see, there exists an enormous, invisible structure that dwarfs everything else in the solar system. A structure so vast that the planets and all their moons and all their rings and all their beauty occupy less than 1,000th of 1% of its volume. A structure that has never been seen and may never be seen directly in our lifetimes, but whose existence is written in the orbits of comets as clearly as words on a page. The Oort Cloud is the solar system's great hidden architecture. Its dark scaffolding, its invisible outer wall. It contains the most ancient, most pristine material in the solar system. Material that has been frozen since the sun was young, since the planets were still forming, since the Earth didn't yet exist. And it extends so far from the sun that it begins to approach the distances between stars. It turns the solar system from a compact disk of orbiting planets into something far larger, far more sprawling, far more impressive, and far more strange than any classroom diagram has ever shown. But just how far does it extend? What does 100,000 AU actually mean in terms you can feel and understand? How does the Oort Cloud compare to the distances between stars? And what does its existence tell us about where the solar system ends and interstellar space begins? These are the questions we need to answer next. Because the numbers involved are not just large, they are the kind of large that changes how you think about space itself. The kind of large that makes even the distance to Neptune, already so vast that light takes over 4 hours to cross it, look like a single step in a journey of 1,000,000 miles. The true scale of the Oort Cloud is where this story goes from surprising to genuinely shocking. And once you see the numbers, once you build them up layer by layer and feel their weight, you will understand why astronomers say the solar system never really ends. It just fades, gradually and imperceptibly, into the space between the stars. Now we arrive at the heart of this story, the part that changes everything. Because understanding the Oort Cloud intellectually is one thing. You can hear the words, you can nod along, you can accept that yes, there's a big cloud of icy objects out there somewhere far away. But truly grasping the scale, truly feeling the distances involved, that's something different entirely. That requires us to slow down and build the picture carefully, layer by layer, comparison by comparison, until the sheer immensity of what we're talking about becomes impossible to ignore. Let's start with what we know. The planets of the solar system, all 8 of them, fit within about 30 AU of the Sun. Neptune, the outermost planet, orbits at roughly 30 AU. That means the entire planetary region, everything from Mercury to Neptune, everything most people think of when they hear the words solar system, spans a diameter of about 60 AU. That's the known, familiar, well-mapped territory. The part we've sent spacecraft to. The part we've photographed and studied and explored with robots and telescopes for decades. The Kuiper Belt extends a bit farther, out to roughly 50 AU from the Sun, perhaps a little more depending on how you define its outer boundary. So, if we're generous, the entire well-studied region of the solar system stretches about 50 AU from the Sun in any direction. 100 AU across, that's the solar system as most people understand it. The Sun, the planets, the Kuiper Belt. Done. Now let's talk about the Oort Cloud. The inner Oort Cloud, sometimes called the Hills Cloud, is thought to begin at roughly 2000 AU from the Sun. Already, that's a jump. From 50 AU to 2000 AU. That means there is a vast region of essentially empty space between the outer edge of the Kuiper Belt and the beginning of the inner Oort Cloud, a gap of nearly 2000 AU where almost nothing exists. No planets, no belts, no known structures, just emptiness, stretching for distances so large that crossing them would take our fastest spacecraft centuries. Let me put that gap in perspective. Voyager 1, the most distant human-made object, launched in 1977, and has been traveling away from Earth for nearly 50 years. As of 2025, Voyager 1 is roughly 165 AU from the Sun. It's moving at about 17 kilometers per second, or roughly 38,000 miles per hour. That's fast. Incredibly fast by any human standard. At that speed, you could cross the entire United States from coast to coast in about 4 minutes. And yet, after nearly half a century of continuous travel at this speed, Voyager 1 has covered only 165 AU. It hasn't even reached the beginning of the inner Oort Cloud at 2000 AU. At its current speed, Voyager 1 would need roughly another 500 years just to reach 2000 AU. 500 more years of travel on top of the nearly 50 it's already completed. And that's just the inner edge, the beginning, the front porch of the Oort Cloud. The outer Oort Cloud is thought to extend to somewhere between 50,000 and 100,000 AU from the Sun. Let's use the more conservative estimate of 50,000 AU for now and come back to the larger number later. 50,000 AU. How long would it take Voyager 1 to reach 50,000 AU at its current speed? Roughly 14,000 years. 14,000 years of continuous travel at 38,000 miles per hour. Think about what that means in human terms. 14,000 years ago, the last ice age was ending. Massive glaciers still covered much of North America and northern Europe. Sea levels were dramatically lower than today. Humans were hunter-gatherers living in small nomadic groups. There were no cities, no agriculture, no written language, no civilization of any kind. People survived with stone tools and animal hides. The entire history of human civilization, from the first permanent settlements to the smartphone in your pocket, fits within the last 10,000 years. Voyager would need more than that entire span just to reach the conservative estimate of the Oort Cloud's outer edge. And if the Oort Cloud extends to 100,000 AU, as some estimates suggest, then Voyager would need roughly 28,000 years. 28,000 years. That takes you deep into the last ice age. Humans were painting the walls of caves at Chauvet in what is now southern France. Vast ice sheets stretched across entire continents. Britain was connected to mainland Europe by dry land because so much water was locked in glaciers that the sea level was hundreds of feet lower than today. agriculture was still more than 15,000 years in the future. Everything that has ever happened in human civilization, every city, every empire, every invention, every war, every discovery, every moment of love or loss or triumph, all of it has unfolded in less time than it would take our fastest spacecraft to cross the Oort Cloud. But distances measured in AU are still somewhat abstract. Let's convert them into something more familiar. Let's talk about light. Light travels at about 186,000 miles per second. 300,000 kilometers per second. It's the fastest thing in the universe. Nothing can exceed it. From the Sun to the Earth, light takes about 8 minutes and 20 seconds. From the Sun to Neptune at 30 AU, light takes about 4 hours and 10 minutes. From the Sun to the edge of the Kuiper Belt at 50 AU, light takes roughly 7 hours. Now. From the Sun to the inner edge of the Oort Cloud at 2000 AU, light takes about 11.5 days. That's nearly 2 weeks for light itself. The fastest thing that exists, just to reach the beginning of the Oort Cloud. Already, we've gone from hours to days. From the Sun to the outer edge of the Oort Cloud at 50,000 AU, light takes approximately 289 days. That's nearly 10 months. Almost an entire year for light to travel from the Sun to the outer boundary of the Oort Cloud. At 100,000 AU, light takes about 1.6 years. A year and 7 months. More than a year and a half for a beam of light, traveling at 186,000 miles per second, covering nearly 6 trillion miles every year, to reach the outermost edge of the Oort Cloud. Let me frame that differently. The distance from the Sun to Neptune, the outermost planet, can be crossed by light in about 4 hours. The distance from the Sun to the outer edge of the Oort Cloud might take light a year and a half. That's a ratio of roughly 3,000 to 1. For every unit of distance between the Sun and Neptune, there are 3,000 units of distance between the Sun and the outer Oort Cloud. The planetary region, everything from Mercury to Neptune, all of it, is less than 1/3,000th of the full extent of the Sun's domain. This means that if you drew the solar system to scale, with the Sun at one end and the outer Oort Cloud at the other, and you made the entire diagram 10 feet long, the region containing all 8 planets would occupy less than 1/25th of an inch, less than a millimeter. You would need a magnifying glass to see it. Everything you've ever learned about the solar system, every planet, every moon, every ring, every spacecraft mission, every photograph, all of it would be compressed into a space too small to see with the naked eye on a 10-foot diagram. The rest of the diagram, the other 9 feet, 11 3/4 inches, would be the Oort Cloud and the empty space leading up to it. Now let's connect these distances to something we discussed earlier. The nearest star to the Sun is Proxima Centauri, part of the Alpha Centauri system, about 4.24 light years away. That's roughly 268,000 AU. The Oort Cloud, at its most distant estimated extent of 100,000 AU, reaches out to about 37% of the way to Proxima Centauri, more than a third of the distance to the nearest star. Even the more conservative estimate of 50,000 AU puts the outer Oort Cloud at roughly 19% of the way to Proxima Centauri, nearly a fifth of the way to the closest star. Think about what this implies. If the nearest star system also has its own Oort Cloud, and there's every reason to believe it does because the same physical processes that created ours should operate around other stars, then the outer edges of the two clouds might actually overlap. Or at the very least, they might come close to overlapping. The space between the Sun and the nearest star might not be empty. It might be populated, however sparsely, by icy objects belonging to one star or the other, or possibly both, drifting in the gravitational no man's land between two stellar systems. The boundary between our solar system and the next one over might not be a sharp line. It might be a gradual, fuzzy transition zone where the Sun's influence slowly fades and another star's influence slowly grows. Let's try some more comparisons to really drive this home. The distance from the Sun to Neptune is about 2.8 billion miles. The distance from the Sun to the outer Oort Cloud at 50,000 AU is about 4.6 trillion miles. At 100,000 AU, it's roughly 9.3 trillion miles. A trillion miles. Thousands of billions of miles. If you tried to drive this distance in a car at highway speed, it would take you more than 17 million years. If you flew in a commercial airplane, it would take over 1 million years. These are not human-scale distances. They're not even civilization-scale distances. They're geological timescale distances, the kind of distances that make sense only when measured against the age of the Earth or the lifespan of species. Let me try another approach to the scale. Imagine shrinking the solar system so that the distance from the Sun to Earth, 1 AU, equals 1 inch. At this scale, the Sun itself would be a tiny dot, less than 1/100th of an inch across. Mercury would be about 4/10 of an inch from the Sun. Mars would be about 1.5 inches. Jupiter would be about 5 inches out. Saturn, roughly 9.5 inches. Uranus, about 19 inches, just over 1.5 feet. Neptune would be about 30 inches from the Sun, 2.5 feet. The Kuiper Belt would extend to roughly 4 feet. Now, at this same scale, where 1 AU equals 1 inch, where the entire planetary solar system fits within a circle about 5 feet across, where would the Oort Cloud be? The inner edge of the Oort Cloud at 2000 AU would be about 167 feet from the Sun. That's roughly the length of an Olympic swimming pool and then some. And the outer edge at 50,000 AU would be about 4,167 feet from the Sun. That's nearly 4/5 of a mile. At 100,000 AU, it would be about 1.5 miles from the Sun. So in this model, the planets fit within a space you could reach across a table. The Oort Cloud extends to 1.5 miles away. You'd need to walk for 20 to 30 minutes just to reach the outer boundary of the Oort Cloud in a model where the entire planetary system fits on your desk. Here's yet another way to think about it. If the distance from the Sun to Neptune were the width of a single human hair, about 3/1000 of an inch, then the distance from the Sun to the outer Oort Cloud would be roughly 10 inches. The planetary solar system would be a hair's width. The full solar system, including the Oort Cloud, would be about the length of a ruler. You couldn't see the planets without a magnifying glass, but you could span the Oort Cloud with your outstretched hands. That ratio, a hair's width to an outstretched arm span, is the difference between the solar system you learned about in school and the solar system that actually exists. These comparisons aren't meant to be precise down to the decimal point. The exact extent of the Oort Cloud is uncertain. We've never observed it directly. The numbers could be somewhat larger or smaller than current estimates suggest. But the fundamental point remains the same regardless of where exactly the outer boundary falls. The Oort Cloud is vastly, overwhelmingly, almost incomprehensibly larger than the planetary region. It's not a little bit bigger. It's not even 10 times bigger. It's thousands of times larger in linear extent and billions of times larger in volume. Volume is where the scale really becomes staggering. Because the Oort Cloud is roughly spherical, its volume scales as the cube of its radius. The planetary solar system, out to Neptune at 30 AU, occupies a sphere with a volume of about 113,000 cubic AU. The Oort Cloud, extending to 50,000 AU, occupies a sphere with a volume of about 524 trillion cubic AU. That's a ratio of roughly 4.6 billion to 1. The Oort Cloud's volume is nearly 5 billion times larger than the volume of the planetary solar system. Even if we just consider the shell of the Oort Cloud itself, excluding the mostly empty interior, the volume is still billions of times larger than the region containing the planets. This means that when you see a textbook diagram of the solar system showing the Sun and 8 planets, you're seeing less than 1/1000th of the solar system's total volume. The diagram is showing you a tiny dot at the center of something enormous and pretending that dot is the whole thing. It would be like drawing a map of the Earth that showed only your living room and labeled it Earth. It's not wrong exactly. Your living room is on Earth, but it's missing almost everything. Now, despite this almost incomprehensible vastness, the Oort Cloud is incredibly empty. We discussed earlier that it might contain a few trillion icy objects. That sounds like a lot, and it is in absolute terms. But spread across a volume of hundreds of trillions of cubic AU, those objects are scattered so thinly that the Oort Cloud is essentially a vacuum with occasional specks of ice floating through it. Let me try to give you a sense of this emptiness. If the Oort Cloud contains 1 trillion objects and occupies a sphere extending to 50,000 AU, then the average amount of space per object is roughly 500 cubic AU. 1 cubic AU is itself an enormous volume, roughly 3.35 times 10 to the power of 39 cubic miles. So each Oort Cloud object, on average, has an almost unimaginable amount of empty space to itself. The average amount of space per object is roughly 500 cubic AU. A single cubic AU is already a volume so enormous that the entire Earth would be an invisible speck inside it. And each Oort Cloud object has roughly 500 of those volumes all to itself. The average distance between neighboring objects might be on the order of 10 AU or more. 10 times the distance from the Earth to the Sun, separating each frozen chunk of ice from its nearest neighbor. If you were standing on an Oort Cloud object and looking out into space, you would see nothing nearby. No other objects would be visible to the naked eye. The nearest neighboring object would be billions of miles away, far too distant and far too small to see. You would be surrounded by stars in every direction, but none of them would be close. No companions, no landmarks, no sense of being anywhere in particular. You would be alone in the darkness, standing on a frozen chunk of ice and rock, a few miles across, surrounded by nothingness in every direction for billions of miles. It would be the most isolated place a human being could possibly be while still technically remaining within the solar system. And yet, these isolated objects are gravitationally bound to the Sun. Each one of them is orbiting our star, completing one enormously slow circuit over millions of years. An object at 50,000 AU from the Sun might take roughly 11 million years to complete a single orbit. 11 million years. The dinosaurs went extinct 66 million years ago. In the time since the dinosaurs disappeared, an object at the outer Oort Cloud would have completed only about 6 orbits around the Sun. These are the slowest orbits in the solar system. Glacial doesn't begin to describe their pace. They move so slowly that their motion would be essentially undetectable even over the span of an entire human civilization. From a human perspective, Oort Cloud objects are stationary, frozen in place, and frozen in time. Let me connect this back to something tangible. Remember how we talked about the Kuiper Belt as being far away? Pluto, in the Kuiper Belt, orbits at about 40 AU from the Sun. When New Horizons flew past Pluto in 2015, it had been traveling for 9.5 years. 9.5 years to reach roughly 33 AU. To reach the inner edge of the Oort Cloud at 2000 AU, a spacecraft traveling at the same speed as New Horizons would need roughly 570 years. To reach the outer edge at 50,000 AU, it would need roughly 14,000 years. To reach the most distant estimate of 100,000 AU, roughly 29,000 years. And that's assuming the spacecraft maintained its speed the entire time, which it wouldn't, because it's gradually slowing down as the Sun's gravity, however feeble at those distances, continues to pull it back. We can also think about this in terms of the Voyager spacecraft's actual experience. Voyager 1 crossed the heliopause in 2012 at roughly 122 AU from the Sun. This was celebrated as a historic milestone. Voyager had entered interstellar space. The solar wind no longer reached it. It was beyond the Sun's magnetic bubble. Headlines around the world declared that Voyager had left the solar system. But had it? The heliopause at 122 AU marks the boundary where the solar wind stops, where the Sun's magnetic influence effectively ends. But gravitationally, the Sun's reach extends far, far beyond that. The Oort Cloud, at 50,000 to 100,000 AU, is still gravitationally bound to the Sun. Voyager 1 at 165 AU hasn't even reached the inner edge of the Oort Cloud. It's crossed less than 1% of the distance to the Oort Cloud's outer boundary. Voyager has left the Sun's magnetic bubble, yes, but it hasn't left the Sun's gravitational domain. Not even close. It has thousands of centuries of travel ahead of it before it reaches the outer boundary of the solar system, as defined by the Sun's gravitational influence. Now let's zoom out one more time and think about what the Oort Cloud looks like from a truly external perspective. Imagine you're an alien astronomer in another star system, looking at our solar system from several light years away. What would you see? You'd see the Sun as a star, a yellowish point of light. If you had powerful instruments, you might detect Jupiter and perhaps one or two of the other large planets orbiting close to the star. The inner solar system, everything within 30 AU, would appear as a tiny dot of activity right next to the star. Beyond that, you'd see essentially nothing for a long stretch. And then, extending outward to 1 or 2 light years from the Sun, you'd detect, if your instruments were sensitive enough, a vast, incredibly sparse halo of icy objects surrounding the star. The Oort Cloud would be the largest visible structure associated with the Sun, even though it's made of tiny objects. The planets would be a pinpoint at the center. The Oort Cloud would be an enormous sphere surrounding everything. From this external perspective, the solar system looks completely different from the way we usually picture it. It's not a flat disk with planets orbiting in neat circles. It's a vast sphere of ice and rock, with a tiny, almost invisible concentration of planets at the very center. The Oort Cloud is the solar system's most prominent feature, at least in terms of the volume it occupies. The planets are an afterthought, a tiny bright cluster at the very core of something enormously larger. This perspective is humbling. We spend so much time and energy studying the planets, and rightfully so, because that's where all the interesting stuff happens. That's where geology and weather and volcanism and oceans and atmospheres exist. That's where life might be found. But in terms of sheer physical extent, in terms of how much space the solar system actually occupies, the planets are practically nothing. They're a rounding error, a footnote. The real solar system, measured by volume, is the Oort Cloud. And here's one final comparison that might help solidify the scale. The distance from the Sun to the outer Oort Cloud, at 100,000 AU, is roughly 1.6 light years. The distance from the Sun to Proxima Centauri is about 4.24 light years. So the solar system, including the Oort Cloud, extends roughly 37% of the way to the nearest star. If the solar system were a city, the planets would be a single building downtown. The Oort Cloud would be the city limits, stretching out to the far suburbs and beyond. And the nearest neighboring city, Proxima Centauri, would be about 2.5 times farther than the city limits. The gap between the edge of the Oort Cloud and the beginning of Alpha Centauri's gravitational domain might be surprisingly small in cosmic terms. The solar system, rather than being a tiny island in a vast ocean of emptiness, is actually a sprawling territory that fills a significant fraction of the space between here and the nearest star. There's another way to feel this distance that goes beyond numbers. Imagine you're standing on an icy object at the outermost edge of the Oort Cloud, roughly 100,000 AU from the Sun. You look around. What do you see? Stars. Thousands of them scattered across a perfectly black sky, sharp and steady, unblurred by any atmosphere. The sky looks much the same as it does from Earth on a clear, dark night. But you search for the Sun, your star, the center of the solar system you still technically belong to. And when you find it, it doesn't look special. It doesn't dominate the sky. It doesn't light up your surroundings. It appears as a bright star, certainly brighter than most of the others, perhaps comparable to how Sirius looks from Earth. A sharp point of light with nothing around it to suggest that 8 planets, hundreds of moons, and billions of living creatures orbit around it. From here, the Sun is just another star in a crowded sky. You could easily lose it among the others if you didn't know exactly where to look, and yet, you're still inside the solar system, You are still gravitationally bound to that unremarkable point of light. You are still, by any physical definition, home. That is how large the solar system really is. It is so large that you can stand within its boundaries and not even recognize your own star. You can be home and feel utterly, completely lost at the same time. This changes the way you think about interstellar distances. When people talk about traveling to the nearest star, they usually think about leaving the solar system first and then crossing a vast empty gulf to reach another star. But the reality is more nuanced. The solar system, in its fullest extent, reaches a significant portion of the way there. You don't leave the solar system and then travel to another star. You travel through the outermost reaches of the solar system for a very long time, and by the time you finally leave our sun's gravitational influence, you're already a substantial fraction of the way to the next star. The Oort Cloud redefines what the solar system is. It takes a compact, well-organized system of planets orbiting a star and reveals it to be the tiny bright nucleus of something vastly larger. Something that reaches across light years of space. Something that blurs the boundary between our star system and the next. Something that contains trillions of frozen worlds, each one a time capsule from the solar system's birth, each one drifting in the darkness at distances so great that even light needs more than a year to reach them from the sun. And all of this raises a profound question. If the Oort Cloud extends this far, if it reaches across such enormous distances, if it fills such an incredible volume of space, then where does the solar system actually end? Is there even a clear boundary? Or does the solar system simply fade away, blending gradually into the space between the stars, with no sharp edge, no clear dividing line, no moment where you can say with certainty that you've left the sun's domain and entered truly interstellar space? That question turns out to have a fascinating and deeply unsettling answer. Because the solar system doesn't end the way most people think it does. It doesn't end with a boundary you can cross or a border you can see. It ends with a whisper, a slow fading, a gradual loss of the sun's grip on the objects that orbit it. And understanding that fading, understanding why the solar system has no clean edge, changes how you think about boundaries, about territory, about what it means for something to belong to our star rather than to the galaxy at large. So where does the solar system end? It sounds like a simple question. The kind of question a child might ask and expect a straightforward answer. You point at a map, you draw a line, you say here. The solar system ends here. But the more you understand about the Oort Cloud and the true extent of the sun's influence, the more you realize that this question doesn't have a simple answer. It has several answers, and they're all different, and they're all correct, depending on what you mean by the word end. This is one of those places where science forces us to think more carefully than everyday language allows. In daily life, boundaries are clear. Your property line is your property line. The city limits are marked with a sign. A country's border is drawn on a map. You're either inside or outside, here or there. But the solar system doesn't work that way. It doesn't have a fence. It doesn't have a sign. It has multiple overlapping boundaries, each defined by a different physical process, each at a wildly different distance from the sun, and none of them is the single definitive edge that most people imagine when they picture the solar system ending and interstellar space beginning. Let's walk through these boundaries one by one, because each one tells us something important about the nature of the solar system and why the idea of a clean edge is so misleading. The first and most familiar boundary is the orbit of Neptune. At about 30 AU from the Sun, Neptune is the outermost planet. For many people, this is where the solar system ends. It's the boundary most textbooks implicitly draw when they show diagrams of the solar system. The planets are the solar system. After the last planet, there's nothing. But as we've already seen, this is profoundly wrong. The Kuiper Belt extends well beyond Neptune. The Oort Cloud extends thousands of times farther. Defining the solar system's edge as Neptune's orbit is like defining the edge of a forest as the first row of trees. There's an entire forest behind them that you're ignoring. The second boundary is more physically meaningful. It's called the heliopause, and it sits at roughly 100 to 120 AU from the Sun. The heliopause is the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun in all directions, finally runs out of energy and is stopped by the pressure of the interstellar medium, the thin gas that fills the space between stars. The solar wind is one of the Sun's most pervasive influences. It flows outward continuously at speeds of several hundred kilometers per second, carrying the Sun's magnetic field with it, creating a vast bubble called the heliosphere. Inside the heliosphere, space is dominated by the Sun's magnetic field and the solar wind. Cosmic rays from elsewhere in the galaxy are partially deflected. The environment is shaped by the Sun. Outside the heliosphere, beyond the heliopause, the interstellar medium takes over. Cosmic rays are more abundant. The magnetic field belongs to the galaxy, not the Sun. The solar wind is gone. Voyager 1 crossed this boundary in 2012, and Voyager 2 followed in November 2018 at about 119 AU. Both spacecraft detected dramatic changes as they passed through. The density of solar wind particles dropped to nearly zero. The density of galactic cosmic rays increased sharply. The magnetic field changed direction. These were real, measurable transitions. The spacecraft had crossed a genuine physical boundary. Many news headlines at the time declared that Voyager had left the solar system. And in one sense, that's true. Voyager had left the Sun's magnetic bubble. It was no longer bathed in the solar wind. It was now immersed in the interstellar medium. But in another equally valid sense, Voyager hadn't left the solar system at all. Because the Sun's gravitational influence extends far, far beyond the heliopause. Gravitationally, the solar system is thousands of times larger than the heliosphere. The heliopause is a magnetic and particle boundary, not a gravitational one. It marks the edge of the Sun's wind, not the edge of the Sun's reach. This is where the third boundary comes in, and it's the one that really matters for our story. The gravitational boundary. The Hill sphere. This is the region of space within which the Sun's gravity dominates over the gravity of other nearby objects, particularly the gravity of the Milky Way galaxy itself and the gravity of nearby stars. Every object with mass has a gravitational influence that extends, in principle, to infinity. Gravity never truly reaches zero. The Sun's gravitational pull gets weaker with distance, following the inverse square law. Double the distance, and the gravitational force drops to 1/4. Triple it, and it drops to 1/9. At enormous distances, the Sun's gravity becomes incredibly feeble, but it never completely disappears. In a perfectly empty universe with nothing else around, the Sun's gravity would extend forever, and objects could theoretically orbit the Sun at any distance, no matter how vast. But we don't live in an empty universe. We live in a galaxy. The Sun is surrounded by other stars, by the overall gravitational field of the Milky Way, by the tidal forces created by the galaxy's mass distribution. At some distance from the Sun, these external gravitational influences become comparable to the Sun's own gravity. Beyond that distance, the Sun can no longer hold onto objects. They get pulled away by the galaxy or by passing stars. They stop being part of the solar system and become part of the broader galactic environment. This distance, the outer limit of the Sun's gravitational dominance, is estimated to be somewhere around 100,000 to 200,000 AU. This is where the Sun's Hill sphere ends. Objects inside this boundary are gravitationally bound to the Sun. Objects outside it are not. They belong to the galaxy. And here's the critical point. This boundary is not sharp. It's not a wall or a fence or a line you cross. It's a gradual transition. The Sun's gravity doesn't suddenly stop at 100,000 AU. It just becomes so weak that other gravitational influences begin to compete with it. At 50,000 AU, the Sun's gravity is dominant but not overwhelmingly so. At 100,000 AU, it's barely holding on. At 200,000 AU, external forces have largely taken over. The transition is smooth, gradual, and fuzzy. There's no specific distance at which you can say with certainty that you've left the solar system. You can only say that as you move farther and farther from the sun's grip becomes weaker and weaker until at some point it's no longer the primary gravitational influence on your motion. But that some point isn't precisely defined. It depends on the direction you're traveling because the gravitational environment isn't the same in every direction. It depends on whether a nearby star happens to be passing close at the moment. It depends on the exact distribution of mass in this region of the galaxy. The boundary shifts and fluctuates over time. The Oort Cloud exists right at this transition zone. Its outer edge is thought to correspond roughly to the limit of the sun's gravitational dominance. Objects beyond a certain distance are no longer bound to the sun and drift away into interstellar space. Objects inside that distance remain in orbit, however slowly and tenuously. The outer Oort Cloud is essentially the population of objects living at the very edge of the sun's gravitational reach. Barely held, easily dislodged, existing in a kind of gravitational twilight between belonging to the sun and belonging to the galaxy. This is why the Oort Cloud is so vulnerable to perturbation. A passing star doesn't need to come particularly close to the sun to disturb the outer Oort Cloud. It just needs to come close enough that its gravity, combined with the galactic tidal force, exceeds the sun's feeble grip on those outermost objects. At distances of 50,000 to 100,000 AU, the sun's gravity is so weak that even a distant stellar encounter can be enough to dislodge objects from their orbits. Some get pushed outward and escape the solar system entirely. Others get pushed inward and begin the long fall toward the sun, eventually becoming the long-period comets we observe. Let me give you a concrete sense of how weak the sun's gravity is at these distances. On Earth, at 1 AU from the sun, the sun's gravitational acceleration is about 0.6 of a centimeter per second squared. That's tiny compared to Earth's surface gravity, which is why you don't feel yourself being pulled toward the sun as you stand on the ground, but it's enough to keep Earth in orbit. At Neptune's distance of 30 AU, the sun's gravitational acceleration is about 900 times weaker than at Earth, still enough to keep Neptune firmly in orbit. At the inner Oort Cloud at 2000 AU, the sun's gravity is about 4 million times weaker than at Earth. At the outer Oort Cloud at 50,000 AU, it's about 2.5 billion times weaker. 2.5 billion times weaker than the already tiny pull you experience from the sun while standing on Earth's surface. At this level of gravitational weakness, almost anything can disturb an orbit. A star passing within a few light years of the sun, something that happens roughly every 100,000 years, can exert enough tidal force on the outer Oort Cloud to change the orbits of millions of objects. The galaxy's overall gravitational field, stretching across the entire disk and halo of the Milky Way, exerts a continuous tidal force that slowly modifies Oort Cloud orbits over millions of years. Even the gravity of the giant molecular clouds that the solar system occasionally passes near during its orbit around the galactic center can have an effect. The Oort Cloud, in other words, is not really a stable, permanent structure. It's constantly being eroded. Objects are being stripped away from its outer edge by galactic tides and stellar encounters. At the same time, the inner Oort Cloud is being slowly depleted as objects are fed inward to become comets. The Oort Cloud we see today, or rather the Oort Cloud we infer today, is what remains after 4.5 billion years of this slow erosion. It was probably much more massive and more densely populated when the solar system was young. Over billions of years, it has been gradually whittled away. The objects we see as long-period comets are the latest casualties of this ongoing process. Some astronomers have estimated that the original Oort Cloud might have contained dozens or even hundreds of Earth masses of material. Today, it probably contains somewhere between 1 and 20 Earth masses. Most of the original material has been lost, stripped away by the galaxy, ejected into interstellar space, or fed inward as comets that eventually evaporated near the Sun. The Oort Cloud is a shadow of its former self, a remnant of a once much larger population of icy bodies, and it continues to shrink, slowly but relentlessly, as the galaxy continues to erode its edges. This raises an interesting thought. If the Oort Cloud is gradually being eroded, then the solar system, defined by the Sun's gravitational domain, is slowly shrinking. Not in any meaningful way on human timescales. The process takes billions of years, but over the life of the Sun, the outer boundary of the solar system has been gradually retreating inward as objects at the farthest distances are stripped away. The solar system is not a fixed, permanent territory. It's a dynamic, evolving structure that changes over billions of years in response to the galaxy around it. This also means that interstellar space is not truly empty. The objects stripped from the Oort Cloud don't disappear. They continue to exist. They drift through the galaxy as free-floating icy bodies, no longer bound to any star. There might be billions or trillions of these objects floating through interstellar space, remnants of Oort clouds from millions of different star systems across the Milky Way. In 2017, astronomers discovered the first confirmed interstellar object passing through our solar system, an elongated body named Oumuamua. In 2019, they discovered a second one, Comet Borisov. Both objects were clearly not gravitationally bound to the Sun. They were passing through on hyperbolic trajectories, visitors from interstellar space, probably ejected from the Oort clouds or planetary systems of other stars long ago. These detections confirmed something astronomers had long suspected. Interstellar space is populated by vast numbers of small icy and rocky objects, the detritus of planetary formation around other stars. Our solar system is embedded in a sea of these objects. Some of them occasionally pass through our planetary region, giving us brief glimpses of material from other star systems. The boundaries between star systems are not clean separations between populated regions and empty void. They are gradual transitions, with objects from different stars mingling in the spaces between. This connects to one of the most profound implications of the Oort cloud's existence. The solar system doesn't have a hard edge. It has a soft, fuzzy boundary that blends gradually into the interstellar environment. If you were traveling outward from the Sun, you wouldn't cross a border and suddenly find yourself in interstellar space. You would pass through the planets, then through the Kuiper Belt, then through a long stretch of mostly empty space, then into the sparse inner Oort cloud, then into the even sparser outer Oort cloud. And as you continued outward, the density of objects belonging to the Sun would gradually decrease, while the density of free-floating interstellar objects would gradually increase. At some point, you'd be surrounded by more interstellar objects than solar objects, but there would be no sharp transition, no moment of crossing, just a gradual fading. The solar system ends the way a campfire's warmth ends on a cold night. You can feel the heat when you're close. As you walk away, the heat fades. At some point, you can barely feel it anymore. But there's no exact step where the warmth ends and the cold begins. It's a gradient. The Sun's gravitational influence fades the same way. Close in, it's overwhelming. Farther out, it weakens. At the Oort cloud's distance, it's barely perceptible, and somewhere beyond the Oort cloud, it becomes so faint that it no longer matters. But there's no sharp cutoff, no border crossing, just a slow, continuous fade. This is why many astronomers say the solar system never really ends. It doesn't terminate. It dissolves. It thins out. It gradually loses coherence as you move farther from the Sun, until eventually there's nothing left to distinguish the Sun's territory from the galaxy at large. The Sun's influence doesn't stop, it just becomes negligible. And the distinction between negligible and zero is philosophically interesting but physically meaningless. At some point, the Sun's gravity is so weak that it takes millions of years to make any measurable difference in an object's motion. Is that object still part of the solar system? Technically, yes, because it's still gravitationally bound, but practically, it might as well be drifting free. This fuzzy boundary challenges our intuition because we're used to thinking in terms of clear boundaries. Inside versus outside, here versus there, ours versus theirs. But nature doesn't always work that way. Many natural structures have fuzzy edges. Earth's atmosphere doesn't end at a specific altitude. It gradually thins out until it blends into the vacuum of space. There's no sharp line between atmosphere and space. Similarly, galaxies don't have hard edges. The density of stars gradually decreases as you move away from the center until the stars thin out and merge with the intergalactic void. The solar system is the same. It has a dense, well-defined core, the planetary region, surrounded by progressively thinner and more diffuse layers, the Kuiper Belt, and then the Oort Cloud, which eventually fade into the interstellar environment with no clear boundary. Understanding this changes the way you think about the solar system's relationship to the galaxy. The solar system is not an isolated island floating in a void. It's a concentration of matter embedded in a larger structure. The Milky Way galaxy provides the gravitational framework within which the solar system exists. The galaxy shapes the Oort Cloud through its tidal forces. Passing stars disrupt it. The solar system's orbit around the galactic center carries it through different environments over hundreds of millions of years. The solar system is a part of the galaxy, not separate from it. The Oort Cloud is the interface between the two, the zone where solar influence gradually yields to galactic influence. When you look up at the night sky tonight, think about what you now know. Those points of light are stars, each one potentially surrounded by its own Oort Cloud, its own vast sphere of icy objects extending light years from its center. The nearest of those stars, Proxima Centauri, might have an Oort Cloud whose outer edge nearly reaches our own. The spaces between stars, which we think of as empty, might be lightly populated with trillions of frozen objects, remnants of ancient Oort clouds, drifting through the galaxy on timescales of millions of years. And our own solar system, the one we call home, the one we've mapped and studied and explored with robots and mathematics, is not the compact, tidy structure shown in textbooks. It is an enormous, layered, multi-scaled system that extends across light years of space. At its center are the planets, compressed into a region so small relative to the whole that it barely registers. Beyond them is the Kuiper Belt, itself just a thin ring compared to what lies farther out. And beyond the Kuiper Belt, extending outward for thousands and thousands of AU, gradually thinning, gradually fading, reaching more than a third of the way to the nearest star, is the Oort Cloud, the solar system's largest structure, its most ancient component, its most mysterious frontier, a vast sphere of frozen worlds that has never been seen and may never be visited, but whose existence transforms our understanding of what the solar system actually is. The Oort Cloud tells us that the solar system is not what we thought it was. It's not 8 planets orbiting a star in a tidy disk. It's 8 planets at the very center of something enormously larger, a spherical territory of ice and emptiness that extends across trillions of miles of space. It tells us that the sun's influence reaches far beyond what most people imagine, extending not just to the edge of the heliosphere at 120 AU, but to 50,000 or 100,000 AU deep into the space between stars. And it tells us that the boundary of the solar system is not a sharp line, but a gradual fade. A slow dissolving of the sun's grip. A gentle transition from our star's domain to the galaxy's. This is the true scale of the Oort Cloud. And this is why the solar system never really ends. It doesn't stop. It doesn't hit a wall. It doesn't cross a border. It just fades, slowly and gracefully, like the last note of a song lingering in a quiet room, growing softer and softer, but never quite reaching silence. The sun's influence stretches outward, weakening with distance, thinning with every passing AU, until somewhere out there, so far from the sun that its light takes more than a year to arrive, the last frozen fragments of the solar system drift in near-perfect darkness, orbiting so slowly that a single circuit takes millions of years, held by a thread of gravity so fine that the passing of a distant star could snap it forever. Those frozen fragments are the Oort Cloud. They are the outermost citizens of the solar system. They have been drifting out there since before the Earth existed, since before life arose, since before anything alive today had a single ancestor. They were scattered outward by the giant planets when the solar system was young, and they've been orbiting in silence ever since. 4.5 billion years of cold, dark, patient drifting at the edge of everything we call home. And every now and then, something disturbs one of them. A distant star passes by, the galaxy tugs gently at its orbit, and that tiny frozen world begins to fall. Slowly at first, then faster, drawn inward by the sun's gravity across distances that take millions of years to cross. It falls past the outer Oort cloud, past the inner cloud, past the vast emptiness between the Oort cloud and the Kuiper Belt, past the Kuiper Belt itself, past the orbits of Neptune and Uranus and Saturn and Jupiter. Its ices begin to warm for the first time in billions of years. Gas streams off its surface, a tail forms, glowing in the sunlight, stretching for millions of miles, and for a few weeks or months, this ancient visitor becomes visible in the night sky of Earth, a comet, a messenger from the edge of the solar system, carrying with it the frozen memory of the sun's birth. The next time you see a comet in the night sky, remember what it's telling you. It's telling you that the solar system is far larger than you ever imagined. It's telling you that beyond the planets, beyond everything familiar, there exists a vast, invisible, ancient structure that dwarfs everything else in the sun's domain. It's telling you that the solar system doesn't end where the diagrams stop. It continues outward for thousands and thousands of AU, fading gradually into the darkness between the stars. The solar system never really ends. It just slowly, quietly, becomes something else. And that frozen visitor streaking across your sky, trailing its glowing tail against the stars, has traveled farther than you can possibly imagine, just to be seen by you tonight. It started its journey at the edge of the sun's reach, in a place so distant that light takes more than a year to get there. It fell inward across trillions of miles of empty space. It crossed the entire width of the planetary solar system in the blink of an eye compared to the millions of years it spent falling. And now it's here, burning briefly in the sun's warmth, shedding the ice it's carried since the solar system was born, before it swings back outward on its impossibly long return journey. A round trip that might take 10 million years. That comet is a bridge between the familiar and the unknown. Between the solar system you learned about in school and the solar system that actually exists. Between the neat little diagram on the classroom wall and the vast, sprawling, fading, boundaryless reality that stretches across light years of space. It's a reminder that the universe is always bigger than we think it is, always more complex, always more surprising, and the place we call home, our solar system, is not the small, tidy thing we once believed it to be. It is enormous, it is ancient, and it never truly ends. Thank you for joining me on this journey to the outermost reaches of our solar system. If you found this exploration meaningful, a like or subscribe would mean a great deal. It helps me keep making these deep explorations of the cosmos. And the next time someone tells you the solar system ends at Neptune, you can smile and tell them it doesn't. It goes on, much, much farther than they think. Past the Kuiper Belt, past the heliopause, out into the Oort Cloud, reaching nearly halfway to the nearest star, fading gradually into interstellar space. The solar system is not a disk of planets. It's a sphere of ice and gravity and darkness, thousands of times larger than the planetary region, ancient beyond comprehension and slowly dissolving into the galaxy that surrounds it. Good night, and may you never see a comet the same way again.